Hey everyone! So, you want to see a little magic trick? What if I told you that I could hit a drum as hard as I possibly can, but you wouldn't hear a single thing? And nope, I'm not talking about hitting the mute button. It's 100% possible. And by the end of this, you'll know exactly how the trick works. All right, let's get into it. To get started, let's set the scene. Imagine we take that drum and we go all the way to the moon. You're standing right there next to me and you watch me hit it. Would you hear that big boom? The answer to this question is the key to unlocking everything we need to know about sound. So, let's figure it out. Okay, first things first. Let's solve piece number 1 of this puzzle. Where does sound actually come from? I mean, think about it. Whether it's a tiny whisper or a massive rocket launch, every single sound in the universe starts with the exact same physical thing happening. And that thing is a vibration. It's a really simple idea when you get down to it. Just picture something moving back and forth really fast, like a guitar string after you pluck it, or your phone buzzing on a table. That rapid to and fro motion, that's a vibration. And believe it or not, that simple little movement is the birth of every sound you've ever heard. And this is happening literally all around you, all the time. When you pluck that guitar string, you can actually see it shaking back and forth. When I'm talking to you right now, my vocal cords are doing the exact same thing. Every sound is born from this back and forth dance. Now, here's the crucial part. This vibration doesn't just happen in its own little bubble. A vibrating object, like this tuning fork here, physically bumps into whatever's around it. In this case, it's water. And when it bumps into those water particles, it passes its energy along, creating a disturbance. This is the exact moment a sound starts its journey. Okay, so we've got a vibration, check, but how does that disturbance travel from, say, a guitar string, all the way across the room to your ear? It can't just teleport, right? It needs some kind of path to follow. Which brings us to the next big piece of our puzzle. And that pathway is called a medium. Now, this is a huge deal for sound. In fact, it's a deal breaker. Sound absolutely has to have a substance to travel through. It could be the air around us, the water in a swimming pool, or even a solid steel beam. No medium, no sound. End of story. And here's a really cool way to picture how it works. Imagine you're in a long, crowded line, and someone behind you gives you a little push. You stumble forward and bump into the person in front of you, who then bumps into the next person, and so on down the line. The push travels all the way to the front, but everyone pretty much stays in their spot. That's exactly how sound moves through the air. It's just a chain reaction of particles pushing each other. Now, all this pushing and pulling creates a really interesting pattern in the air. The spots where the particles get all bunched up together have high pressure. We call those compressions. And the spots where they spread out again have low pressure. We call those rarefactions. So really, a sound wave is just this pattern of compressions and rarefactions traveling through the air. So we figured out that this traveling disturbance is a wave. But, scientists love to be specific. And it turns out there are a couple of different types of waves. To really get what sound is, we need to know exactly what kind of wave we're dealing with. First off, because sound needs that medium, that stuff, to travel, it's called a mechanical wave. This is a really important category. It's what separates sound from something like light, which is an electromagnetic wave, and can travel through the totally empty vacuum of space with no problems at all. Okay, let's break this down because this is a super cool distinction. In a transverse wave, the particles themselves move up and down, while the wave of energy moves forward. Think about shaking a rope. Your hand goes up and down, but the wave travels away from you. But in a longitudinal wave, the particles move back and forth in the exact same direction the wave is traveling. The perfect example is pushing a slinky. The little compression travels forward, parallel to the slinky itself. And you guessed it, that is exactly what sound is. It is a longitudinal wave. Those air particles get pushed back and forth in the very same direction that the sound is traveling, just like that domino effect we talked about. Now, if your brain is spinning trying to keep those two straight, don't worry, I got you. There's this fantastic little memory trick. Just remember the sentence, P.T. Sir told me to sleep later. The P and T tell you that perpendicular motion is a transverse wave, and the S and L tell you that straight or parallel motion is a longitudinal wave. It's a great way to lock it in your memory. All right, we've gathered all the evidence, we know what sound is, we know how it's made, and we know how it travels. I think it's time we go all the way back to our original question and finally solve the mystery of the silent drum on the moon. Let's just walk through it, step by step. 1. We know sound starts with a vibration. Hitting a drum definitely makes it vibrate. So, check. 2. We know that vibration needs a medium. It needs particles to pass its energy along. But 3, the moon is in space, and space is a vacuum. And what's a vacuum? Well, it's a place with pretty much no particles at all. So there's the big reveal. Even though the drum is vibrating like crazy, that energy is stranded. It has nowhere to go. There are no particles to start that chain reaction. The sound is created, but it can never reach your ear. And that's the magic trick. The sound isn't gone, it just can't travel. So now we totally get how sound works, but for our final piece of the puzzle, let's crack the code on why sounds are so different. You know, why is a whisper completely different from a shout? Or why does a flute sound so different from a big tuba? It all comes down to 2 simple properties of the wave. First, there's amplitude. That's basically the height, or the power of the wave. A bigger push on the particles creates a bigger amplitude, and our brain hears that as a louder sound. Then you have frequency. That's how fast the wave is vibrating. How many waves pass by a certain point every second. The higher the frequency, the higher the pitch our brain perceives. This little table sums it all up perfectly. Amplitude gives you loudness, the difference between soft and loud. And frequency gives you pitch, the difference between low and high. Seriously, these 2 properties are the basic building blocks of every single sound you have ever heard. Okay, so let's do a super quick recap. Sound is energy, and it's created by vibrations. It travels as a longitudinal wave, and this is the big one, it absolutely must have a medium to travel through. Finally, its 2 main characteristics are amplitude, which determines how loud it is, and frequency, which determines its pitch. And that leaves us with one of the all-time great riddles. Based on everything we've just learned, that sound is a physical vibration traveling through a medium, which then has to be interpreted by an ear. What do you think? If a tree falls in a forest and no one is there to hear it, does it actually make a sound? You've got all the tools now. I'll let you decide. Thanks for watching.